Hello, my darlings. Okay, so today we're going to talk about inverses and the identity matrix. Now, before we get there, I want to do a little bit of multiplication. So we're going to multiply these two matrices. We have a 2 by 2 matrix times a 2 by 2 matrix. Since the number of rows from the first matrix is the same as the number of columns from the second matrix, we will be able to multiply them. We're going to take the rows from the first and the columns from the second. So we're going to open up a new matrix. Now, in this top spot in the upper left, we are in row 1, so it's going to be 2 times something plus 3 times something, because that's the first row. We are also in column 1, so we're going to take the first column of the second matrix, 1 and 0. Now, if we move down, we're now in row 2, so we're going to take the 4 times something minus 2 times something. And we're still in column 1, so we're still taking the first column from the second matrix. Now I ran out of rows, so I'm going to go back up to the top. I'm back in row 1, so it's 2 times something plus 3 times something. But this time I'm in column 2, so I'm going to take the 0 and the 1. When I move down, I'm in row 2, which means I have a 4 times something minus 2 times something. And I'm still in column 2, which is 0, 1. I'm at the bottom, so I move up. However, I don't have a third column, so now I am done. So now we need just a little bit of arithmetic here. Okay, 2 times 1 is 2, plus 3 times 0 is 0, which means that upper left-hand number is just going to be 2. If we go down, 4 times 1 is 4, minus 2 times 0 is 0. That's going to leave us with a 4. Then if I go to the upper right, 2 times 0 is 0, plus 3 times 1 is 3. That's going to give us 3. Then I move down, 4 times 0 is 0, minus 2 times 1 is 2, and that's going to give us a negative 2. That should look familiar. Doesn't that look just like that, right? This is the original first matrix. So if you think about regular arithmetic, if we had something like 5 times a number gave us the answer 5, what would that magic number be? It's 5 times 1, and that's because 1 is the identity for multiplication. Well, guess what we just learned? This matrix 1, 0, 0, 1 is called the identity matrix. And it's usually denoted with a capital I. Now, that said, that's a 2 by 2 identity. If we have a 3 by 3 matrix and we want the identity, it'd be 1, 0, 0, 0, 1, 0, 0, 0, 1. So the identity matrix has 1s on the diagonal, starting at the upper left corner, and zeros everywhere else. Okay, so it doesn't matter what size matrix you need. Now notice it's going to be square. Doesn't matter what size, but you'll be able to now find the identity matrix. Let's multiply these two matrices. So again, from the first matrix, we're going to take the rows, which are 3, 0, and 1, 4. And from the second matrix, we take the columns just like RC Cola, rows then columns first. All right, let's open up a matrix. Now at this upper left-hand corner, we are in row 1. So I'm going to take 3 times something plus 0 times something. Now since I'm in column 1, my somethings are this column here, 1/3 and negative 1 over 12. And if I move down, I'm now in row 2. So I have 1 times something plus 4 times something. and I'm still in column 1, so it's 1/3 and negative 1/12. If I try to move down, I'm out of rows in my first matrix, so I can close that off here. And now I'm going to go back up to the top, and I'm back in row 1, so it's 3 times something plus 0 times something. Now my somethings, this time I'm in column 2, which means I have a 0 and a 1/4. If I move down, I'm in row 2, so I have a 1 times something plus 4 times something, and my somethings come from row 2, 0 and 1/4. If I go back up and move over, I don't have a third column, so I am done here. Now we just need to do a little bit of arithmetic. 3 times 1/3 is 1, plus 0 times negative 1/12 is 0. That's going to give us 1. Now if we go down, row 2, column 1, 1 times 1/3 is 1/3. 4 times negative 1/12 is negative 4/12, which is negative 1/3, and they're going to add to 0. Now if I go back up, 3 times 0 is 0, plus 0 times 1/4 is 0, so that gives us a 0 up there. And in the bottom, 1 times 0 is 0, plus 4 times 1/4 is 1. That's going to give us a 1. That should look familiar. That's the identity matrix. Well, wait a minute. Let's think about regular arithmetic for a minute. If we had something like 5 times something gives us the identity 1, what would we have to multiply by? We would have to multiply by 1/5 because that's its multiplicative inverse, which means these two matrices that we started with are inverses. So these two matrices, 3, 0, 1, 4, 1/3, 0, negative 1/12, 4, are what we call inverses because the product is the identity matrix I. Okay? A matrix can only have an inverse if first it is a square matrix, but not every square matrix has an inverse. We'll look at when they do and when they don't. Now, because it is an inverse, we know that the product of the matrix A and the inverse of matrix A, which we write A raised to the negative 1, but we don't read that as A raised to the negative 1. We read that as A inverse, or the inverse of A. So when we multiply A times A inverse, we get the multiplicative identity matrix, which we call I. So A times A inverse is I, which means back up here in this problem, this first matrix would be A, this matrix is A inverse, and A times A inverse gives us that identity I. Okay? So the next thing up is determine if the matrices are inverses. So how do you tell if the matrices are inverses? If they're inverses, when you multiply them, what are you supposed to get? Do you get the identity matrix I? So here we go. We're going to write these matrices. 1, 3, 2, 5 times negative 5, 3, 2, negative 1. We're going to take the rows from the first matrix, and we take the columns from the second matrix, and let's see what we get. So when we start, upper left-hand corner, we're in row 1, so it's 1 times something plus 2 times something. We're in column 1, so we're going to take column 1, which is negative 5, 3. Now if I move down, I'm in row 2, which is 3 times something plus 5 times something. I'm still in column 1, so I still have negative 5, 3. If I try to move down, I'm out of rows, so I'm going to close off that matrix at the bottom. I'm going to go back to the top. I'm in row 1, so it's 1 times something plus 2 times something. And my somethings now are coming from column 2, which has a 2, negative 1. When I move down, I'm in row 2, which is a 3 times something plus a 5 times something. And my column 2 is still 2, negative 1. So I'm at the bottom. I try to go to the top, but I don't have a third column, so I can close off that matrix. Now, let's do a little bit of arithmetic. 1 times negative 5 is negative 5, plus 2 times 3 is 6, and negative 5 plus 6 is 1. And remember, yes, it's okay if you go from that matrix down to this one, but I do want you to show me your work for the multiplication, so this matrix does need to be there, okay? Let's see, now we have 3 times negative 5 is negative 15, plus 5 times 3 is 15, and they add to 0. So far, so good. Upper right, 1 times 2 is 2, plus 2 times 1 is negative 2. That adds to 0. And then 3 times 2 is 6, plus 5 times negative 1 is a negative 5, and 6 minus 5 is 1. This is the identity matrix, so our answer is yes, they are inverses. Let's try another one. So now we've got the 2 by 2 matrix, 4, 3, 6, 4, times this matrix, 3, negative 2, negative 2, 8, and we are going to take the rows from matrix 1, and we're going to take the columns from matrix 2, always in that order, and we're going to start multiplying. So in the upper left-hand corner, we are in row 1, so we're going to use the 4 times something plus the 6 times something. We're in column 1, so we're going to take this column, 3, negative 2. Now when I move down, I'm in row 2, which is 3 times something plus 4 times something. I'm still in column 1, so I'm still using 3, negative 2. If I try to move down, I'm out of rows in matrix 1, so I close that off at the bottom. Now I go to the upper right corner, and I'm going to use row 1 again, 4 times something plus 6 times something, but this time I'm in column 2, so I have a negative 2, 8. When I move down, I'm in row 2, which is 3 times something plus 4 times something, and my second column is negative 2, 8. Now when I try to go up to the top again, I am out of columns, so therefore I'm done. Okay, we're going to do a little bit of arithmetic now. 4 times 3 is 12, 6 times negative 2 is negative 12, and we get a 0. Now I know right now this is not going to be the identity because this top corner is supposed to be what number? It's supposed to be a 1. So I already know the answer to my question, but you know me, I can't leave this half done what it looks like. 3 times 3 is 9, and 4 times negative 2 is negative 8, so that's going to give us a 1. The 1 is the bottom position, which is supposed to be a 0. 4 times negative 2 is negative 8. 6 times 8 is 48. 3 times negative 2 is negative 6. Plus 4 times 8 is 32. Oops, I forgot to do those. So negative 8 plus 48 is 40. Negative 6 plus 32 is 26. This is definitely not our inverse matrix, so our answer is no. These two matrices are not inverses. Okay? All right, so we know how to tell if two matrices are inverses, but how do we actually find the inverse of a matrix? Well, if we have this matrix A, which is ABCD, then its inverse is 1 over the determinant times what we call a transposed matrix. Now, for the transposed matrix, what has to happen is on this diagonal from the upper left, this downward diagonal, those numbers switch. See how they change positions? Okay. And then on the right diagonal, or the upward diagonal, if you prefer that terminology, the CB, we negate them. They don't change, they negate. So we switch on the downward diagonal or the left diagonal, and we negate on the right or the upward diagonal, okay? Now, important to realize here is if the determinant is 0, this first part would be 1 over 0. You can't have that because it's not defined, and therefore the matrix would have no inverse. Remember, I told you earlier that you have to have a square matrix in order to have an inverse, but not every square matrix has an inverse. Okay, so if the determinant of the matrix is 0, there is no inverse. So let's go step by step through this process. So we're going to find the inverse for the matrix 2, 3, 5, 5. So the first step is to find the determinant. So we're going to write this as the determinant of 2, 5, 3, 5. Now remember, when we do this, we multiply on this diagonal minus, we multiply on this diagonal, and we're going to have 10 minus 15, which is negative 5. So that means that our inverse, we're going to start with 1 over negative 5. Then we're going to open up a 2 by 2 matrix, okay? But on this downward diagonal, we're going to switch. So now the 5 is the upper left and the 2 is the bottom right. And then on this diagonal, we're going to negate them. So this upper right is a negative 3 and the bottom left is a negative 5. Now we still have to do some multiplication because we have this scalar here. We need to multiply the scalar. So we multiply each entry by 1 over negative 5, or just negative 1/5. So 5 times negative 1/5 is negative 1. I'm going to work down. Negative 1/5 times negative 5 is a positive 1. Negative 1/5 times negative 3 is a positive 3/5. Negative 1/5 times 2 is a negative 2/5. And that means that this matrix right here is our inverse matrix. See, that's not so difficult to do, right? That's doable. Why do we need to find the inverse of a matrix? Right now I'm teaching you the process, but you don't really see a point. If you're working with equations that have matrices, you might need to cancel out a matrix to find your solution. And if you can multiply that matrix by its inverse, you'll be able to solve the equation. So this is an important step for us in being able to solve equations or systems of equations. I know you know how to solve systems of equations algebraically by substitution or elimination, or graphically by finding points of intersection. However, what this method with matrices that we will learn soon will let you solve equations with many, many, many variables and many, many equations, which is something that in high-level mathematics or applied mathematics is something that people need to be able to do. Also, for you guys, it's a very quick, once you master it, it's a very quick, easy way to solve a system of equations, okay? But that's for another time. This way you know where we're headed and why we're doing this. Let's find the inverse for this matrix. So first step, we're going to find the determinant for 3, 1, 0, 4. So this diagonal first, 3 times 4 minus, now we're going to do this diagonal, 1 times 0. So 3 times 4 is 12, minus 1 times 0 is 0. Our determinant is 12, which means that when we want to find our inverse, we start with 1 over 12. Now we're going to set up a 2 by 2 matrix. On this diagonal, we switch the numbers, and on this diagonal, we negate the numbers, but when you negate 0, you still get 0, okay? Now, we multiply through our scalar. 1/12 times 4, that's 4/12, which reduces to 1/3. 1/12 times -1 is -1/12. 1/12 times 0 is 0. 1/12 times 3, that's 3/12, which reduces to 1/4. This here is our inverse matrix. I have one more example I want to do with you. We're going to find the inverse for this matrix. So we start with the determinant 8, -4, 4, -2. So first we use this diagonal, 8 times -2 minus, now we use this diagonal, 4 times -4. So 8 times -2 is -16, and a -4 times a -4 is a positive 16, which gives us 0. So that should be ringing alarm bells for you, okay? Because I already told you what happens with that. So if you go to try this, it's going to be 1 over the determinant, which is 1 over 0. That's undefined. So 1 over 0 times any matrix is not going to have an answer. That means we have no inverse. Now, that kind of matrix has a special name. That's what we call a singular matrix. A singular matrix is a matrix that does not have an inverse, and that is because its determinant equals 0. Okay, so if the determinant is 0, the matrix does not have an inverse, and that's what we call a singular matrix. All right, guys, so we talked about the identity matrix, and we talked about what it means to be inverse matrices, as well as how to find them for 2 by 2 matrices. All right, guys, have a great day, and I'll see you soon. Bye.